Hi, and welcome back to Advanced Machine Learning. I'm Victor Banks, and right now we will talk about the follow-the-leader algorithm on so-called online linear optimization problems. And first of all, we will get to know what these online linear optimization problems are. And we will see that the follow-the-leader algorithm might fail on exactly this type of online learning problems, and we will try to understand why this is the case. So, what are online linear optimization problems? And similar as online quadratic optimization problems, they are simply characterized by their loss function. Namely, the loss function is simply a linear loss function in the sense that a pair of action and environmental data points are mapped to their inner product, so A transpose Z. So you see why this is called a linear loss, because it's linear, well, in the action input, in the action component, but also linear in the environmental data point component. And these type of losses are quite important, as we will also see later on in the online learning world, but they are also important for modeling certain real-world problems, especially when it comes down to path planning. So path planning problems can very often expressed in this way, that you have here more or less the costs. Z are then the cost for taking a specific route, and this is then summing up with the points on the path, which are characterized by the action component A in a sense. All right, and we will have a look at now an example, a very simple example for an online linear optimization problem, where the action space is one-dimensional. It's simply the interval ranging from -1 to +1. And our environmental data points are given as follows. So the very first environmental data point is -1/2. And then it's alternating between +1 and -1, depending on whether the time step is even or odd. And we will see that the follow-the-leader algorithm will fail in the following sense, namely, it doesn't matter how we choose the first action. So we can use the best action available for this first environmental data point, which we'll also use later on. But still, the cumulative loss of the follow-the-leader algorithm will be exactly or even greater than the time horizon -3/2, which is obviously linearly growing with the time horizon. But the best action in hindsight, in fact, will have a cumulative loss of simply -1/2. And here, by the way, you also see now an example of a loss function where you can also have negative values, not only positive values. You will see it later on. If we, for instance, have an odd time step and we choose an action which is positive, a positive number, this loss here will be negative. But combining these two, so that the cumulative loss will be at least t-3/2, and the best action in hindsight has a cumulative loss of -1/2. It is meaning, if we combine the two, that the cumulative regret of the follow-the-leader algorithm will be t-1, and it is linearly growing with t. And this is exactly what we don't want in the online machine learning world. We want an algorithm, an online learning algorithm, which has a regret guarantee which is sublinear, yeah? So growing slower than linear with respect to the time horizon t. Okay, how can we see this, that this here is true? So let's first of all start with the action rule of the follow the leader algorithm. So recall, in time step t plus 1, what is the action taken by the follow the leader algorithm? It's the one or one of the actions which is minimizing the cumulative loss over all seen environmental data points so far. Now we plug in our definition of the loss. So our loss, remember, it's the linear loss. So it's A transpose Z. We are in the very simple setting that the action space calligraphic A is one-dimensional, and the Z, the environmental data set, well, it's in this case it's even easier because there are only 3 realizations, namely it can be -1, -1/2, and 1. So taking these things into account, we can here plug in the definition of the loss function, taking into account that we are in the one-dimensional case, so the A is one-dimensional, the Z is one-dimensional, so this inner product is simply multiplying A with Z. So if we plug this in here, we would have A times ZS. A is independent of the summation index S. We can write it in front of the sum, and this is why the A is showing up here. Now, if we look at this term, yeah, and ask for which A in our action space, ranging from -1 to +1, is minimizing this expression here, we see it's boiling down to making a statement about the sign of this sum here over the environmental data points seen so far. Namely, if the sum has a positive sign, so this here is strictly greater than 0, then what should we do if we want to minimize this here by choosing an appropriate A? We should use the smallest possible A, because then the entire term is as small as possible. And the smallest possible A we can choose regarding our action space is the -1. With the same argument, but only now reversed sign of the sum over the environmental data points, assuming they are negative, strictly negative, we see this thing here is as small as possible, or the entire thing, if we multiply with A, is as small as possible if we choose here the largest A we could have, the largest positive A, because this here is negative. And the largest one is, due to our action space, the +1. And then the edge case, let's say, is when the sum is exactly 0, then we can choose whatever we want, because multiplying something with a 0 is still a 0, so the expression here will always be the same. But for our example, this will be of no interest, this case. So only these 2 cases are interesting. Okay, so we see the follow the leader algorithm will essentially be -1 or 1 in this example. So let's have a look at our concrete example, in the sense that we now look at exactly the evolution with respect to the environmental data points we generate. So in the very first time step, we know the environmental data point will be -1/2 by construction. And now recall the very first action of the follow the leader algorithm is arbitrary due to our basic online learning protocol, where we first choose the action and then only see the data point. So let's say we choose the best action for the first environmental data point. Well, again, taking into account that we are looking at the linear loss, the best action we could take if -1/2 is the environmental data point is the 1, because then we are having the smallest possible linear loss. Linear loss again is multiplying the action with the environmental data point, and we make it as small as possible if we multiply the -1/2 with the largest positive value we can have. Now, what's the cumulative loss? Well, we have suffered a loss of -1/2, so we are doing good right now. And let's keep track of the sum over the ZS. So the environmental data points, and the first one was -1/2, so we have here -1/2. Let's go to the next time step. Now we know the sum over the environmental data points is -1/2. So we are, in this case, when we want to compute now the next action of the follow the leader algorithm, so we know from our previous consideration it will be +1. Now by construction, the environmental data point will be +1 as well. So if we multiply the two here, we get a linear loss of 1. 1 times 1 is 1. So what happens with our cumulative loss? Well, we have to add the 1 to the previous cumulative loss, which was -1/2. We keep track of the sum over the environmental data points, so we have to add to this -1/2 this 1 here, and we get a +1/2. Now, this is our current sum over the environmental data points. It's positive, so we are in this case, meaning that we will take as an action, or the follow the leader algorithm will take as an action -1, but the environmental data point by construction will be -1 as well. Multiplying the two, which we need to do to compute the linear loss, is giving us again a 1. We add this 1 to our previous cumulative loss, end up with 2 minus 1/2. We update the sum over the environmental data points, add to the 1/2 the -1, get the -1/2, and well, if we do this now till we reach the time horizon, you see the pattern in here. So the action by the follow the leader algorithm will always be either 1 or -1, depending on whether the t is odd or even. So if it's even, it's a +1. If it's odd, it's a -1. But the environmental data point will have the same sign in front of the 1. So it will be always either both positive or both negative, meaning that in both cases, even or odd, we have a linear loss of 1 each time. And well, when we are in time step capital T, we are adding up then t minus 1 once here to the very first optimal action in the first time step, where we had this linear loss of -1/2, and the for sake of completeness, the sum over the environmental data points will be -1/2 to the power of t. Okay, now so you see here, indeed, the cumulative loss will be t minus 3/2, because we have used in the very first time step the best action we could get. Yeah? So if we would have used here something different, we would have suffered a higher loss, but the choices after that wouldn't have been affected by this, because the next choice is only depending on the environmental data points, or the sum over the environmental data points and their sign. What would be the best action in hindsight? Well, we have to find the infimum over the action space A of the cumulative loss for all of these actions. And well, it's essentially the same consideration as here before. So we have here the sum over the environmental data points, which will be, after reaching the time horizon t, will be minus 1/2 t. And well, in either case, what you will do is you will either choose a +1, if the t is odd. So if you have here in fact a minus 1/2, and the other way around if it's even, then you would choose a -1. And in both cases, the minimum value will be minus 1/2. So you will multiply here the minus 1/2 to the power of t with essentially the reversed sign. So the best action is having a cumulative loss of minus 1/2, as we saw before. So taking these two together, we see the regret will be growing linearly with the time horizon. So we see here the problem of the follow the leader algorithm, so that it can fail for these type of problems where we have a linear loss function which is giving rise to an online linear optimization problem. But we saw before it's performing quite well for online quadratic optimization problems where we had this quadratic loss function. And the reason for that is the quadratic loss function, which is underlying online quadratic optimization problems, is essentially beneficial for the follow the leader algorithm, as the action rule is quite stable. So it's not jumping from one extreme to the other. In the online linear optimization problem, where we have this linear loss function, there you can have this behavior, as we just saw in the example. We were jumping from one extreme, from a +1 to a -1. So we went from one end of the action space to the other. So in other words, it's not stable, the action selection in the online linear optimization problem scenario. And well, we have to remark again that this example we had here is of course specifically designed to show that the follow the leader algorithm can fail for online linear optimization problems, where you have a high variety, so where the environmental data points are changing quite drastically. This is also how the example was constructed, that the environmental data points are jumping from one extreme to the other, which is not always the case in the real world, that you have this kind of variation. So it might be the case that the follow the leader algorithm in practical application performs quite well for this task of online linear optimization problems, but theoretically, as we just saw, there is a flaw. So it can have a linear regret, which is something we want to avoid. And the question is, of course, how can we avoid this? How can we modify the follow the leader algorithm such that we don't suffer, in the worst case, a linear regret for online linear optimization problems? And this will be the question for the next video.